Hello and welcome to another episode in this PFAS series. Today I'm going to talk about one of the questions that comes up, the first questions people ask when you start discussing PFAS and the scope of the problem and how much is out there is treatment. What can be done? What's being done? How do we get rid of something that we keep calling a forever chemical? Drinking water especially is the key topic when we talk about removal of PFAS, but of course, PFAS in any media like groundwater or surface water or soils or food would all need some sort of remediation or treatment. Today, I'm focusing on drinking water because that's the number one source to us in our in human exposure. But these treatments can apply to other types of materials besides just drinking water. So removal of PFAS, very important. So I introduce for the second time our PFAS. If we want to get rid of this PFAS, we will need to remove it from the system using something that it likes to stick to. So in this case, we're using the actual chemical properties of PFAS, or of PFAS in general, their affinity to want to stick to nonpolar things. They have a nonpolar tail there, so that's how the activated carbon works. They use nonpolar interactions to pull it out. This is just like charcoal. Reverse osmosis, which is the most effective treatment for removing and filtering water, but it's also the most expensive. It utilizes water pressure to force the water through a membrane that the PFAS just can't get through. Our PFAS is just too big to get through that membrane. Also, polymeric sorbents that are designed to even specifically attach certain, like PFOA, have been produced. And these are pretty expensive. They're pretty specialized, and there's no way to regenerate them. They're also kind of expensive. I'm kind of going through the most common methods of removal here. Ion exchange, that head group, the charged head group on PFAS, such as the horn of the PFAS there, that negative charge. They like to stick to things with an opposite charge, so you use ion exchange to kind of hold based on those interactions. So this is what's currently used out there, and these are all to make your drinking water cleaner and safer. These are what water quality districts will use to get down below some of those EPA mandated levels or below some of their own levels. In Chemical and Engineering News by ACS, they showed that a water municipality in North Carolina to put in an activated carbon system for the purpose of PFAS treatment cost them $46 million and will cost them $3 million per year. So even activated carbon, which we see as the cheapest and kind of best value way to do this, is very expensive. That activated carbon has to be incinerated and then regenerated and then replenished because it gets overloaded. We're not destroying PFAS here. We're just sticking them to something and actually concentrating them. That's one of the biggest problems with these treatment systems is none of these destroy PFAS. All of these concentrate PFAS into a very concentrated waste stream. And then what I mentioned a second ago, where does the PFAS go? We're sticking to all this media, but it's still a PFAS. It's still there, and it has to go somewhere, right? If it just goes to a landfill, what's going to happen? It'll eventually leach back into the environment. So what are we going to do? How are we going to destroy our PFAS? And to know what PFAS says about this, he says, I roll, #CFBond. PFAS is pretty arrogant, and it was just born a few weeks ago when I drew it. So it's definitely a child of this new generation of emojis and hashtags. So PFAS has a little bit of attitude. CF bond, it thinks the CF bond's going to protect it. And it's correct, but also if you apply enough energy to anything, you will destroy it. Some of the things that have been used to break down PFAS, electrochemical oxidation. So this is using a lot of energy in the form of electricity. You can run water past these electrodes and degrade the PFAS. Same thing, chemical oxidation. You can use things like persulfate and permanganate to attack the compound and break it down into smaller pieces. Ultrasonication, again, you're using energy in the form of sound waves. Thermal degradation, energy again. You're probably seeing a common theme with all of these different mechanisms to break down. What do they require? They require energy. It took a lot of energy to build this molecule to do, and remember, it's electrochemical fluorination that they use to synthesize these compounds, and it takes a lot of energy. So we at least need that much energy to break them down. All of these have some pros and cons. All of these treatment modalities use energy and are expensive. It's much easier just to lock the waste in a barrel and leave it somewhere forever, like we do with radioactive waste. It's kind of thought in the field that the best way to dispose is thermal, the last one I showed there, using incineration. But they're not necessarily testing, like I said earlier, not necessarily testing for all of the potential byproducts. They're assuming it all goes to carbon. They're assuming it all goes to fluoride or HF. They're assuming it's elemental, but it's a tricky assumption. What is probably happening, and what is definitely happening on the way to complete degradation, is our PFAS is getting broken up into baby PFASuses. So a baby PFAS is a baby PFAS, because it's no longer a PFAS. That would be octane sulfonate with 8 chain links. So these little ones are just a variety of whatever else could be happening. For these treatments, they would hope that none of these baby PFAS occur, but unless you have an application and a method to constantly be testing to make sure you're not releasing these, you could be releasing all of these into the environment through flue gas, back into the water. Who knows? It depends on your treatment modality, but some of these are even greenhouse gases. So we're taking one problem and making another problem. We're using energy, that's a carbon footprint, and then using that to maybe form some greenhouse gases. That could be a big problem. So far, there's no golden ticket for degradation. Once somebody makes some good methods, thoroughly tests them, validates them, and institutes a way to ensure that they keep working over time, whoever makes that is going to make a lot of money, but it still isn't there yet. We are using energy to make a process that may be incomplete. So how can you ensure complete destruction? Testing. The unfortunate part of testing is there's no one size fits all for testing. There's no one method that you can just test for any PFAS. So it's a big challenge. What can you do on your own is another question you get. And in-home PFAS removal, so Brita filters, charcoal filters, they are effective, but they're not the most effective, and over time they will lose their effectiveness. So it's kind of variable. In-home reverse osmosis systems have been shown to be very, very good at completely removing PFAS, but unless you're handy, you have to have a plumber install these. You have to replace the filters on these every once in a while, and they're not cheap, $150, $500, some are $1,000. This is great if you can afford one. It's unfortunate that many people in our country and across the world wouldn't have access to this because they can't afford it. That's causing a little bit of, I think, environmental justice issues there. And definitely that kind of thing should be addressed in the future. But this is a way to protect yourself, to protect your family. If you can spare the extra money, it could be worth it in the long term for human exposure and toxicology. So what can be done in the big picture about PFAS treatment? Well, technology is getting better. There's always new papers, there's always new startups, there's always new companies helping that breakdown, helping the treatment, helping the filtration. We want it to be more efficient. We don't want it to use all this energy and carbon emissions. That is worsening one environmental problem to solve another environmental problem, and that's not good. The real way to end this PFAS cycle is to eliminate the source. I talked about this in another episode. The current cycle is we have an industrial application and we use a PFAS compound to fill that role. That one gets banned or phased out, replaced by another one, banned, phase out, and the cycle just continues. This is where we really have to clean up PFAS, is find alternatives to these applications that are not persistent and that will not just break down into other PFAS. Okay, so that's all I have for today. And hopefully that was an overview. I know I did not go into a whole lot of detail about how those treatments work, but you can just remember water municipalities are doing everything they can do to get PFOA and PFAS down below 70 ppt, but there's still a lot out there, and there's still a lot that's not being cleaned up or tested for. Again, I encourage science to move forward with this and for everyone to keep up with the science. And I encourage you, if you watch this video, to like and subscribe because that helps me out. Thank you very much for your time, and we'll see you next time. Bye.